Hey, welcome back to your favorite calculus class. Going to take a look at inverse trig functions. So this is just kind of a review. In fact, let me look at the visuals here. If you remember the inverse trig functions, we had to take the original sine function and cut it off between negative pi halves and pi halves. And this is what our arc sine looked like. We took the original cosine function, and since it was not one-to-one, we cut it off between 0 and pi. And this is, once we flip-flopped all those xy values, that's what the arc cosine looked like. The arc tangent we cut off between negative pi halves and pi halves and flipped all those xy's. That's what our arc tangent looked like, and so on. There's the arc cosecant, arc secant, and arc cotangent. So let's do a review, couple review problems here. If we have the arc sine of negative a half, we're gonna evaluate it. So I'm gonna set it equal to theta. Well, if this is true, then that means that the sine of theta, since they're inverses, would equal negative a half, right? The input and output switch places. And this is where theta is between pi halves and negative pi halves, right? So I say, well, between pi halves and negative pi halves, the only place where I have the sine of theta being negative a half would be at negative pi 6, right? I'd have to rotate negative pi 6. It's 11 pi 6, but again, it's got to be between pi halves and negative pi halves, so it's negative pi 6. So sine of negative pi 6 is negative a half. In other words, theta is negative pi 6. In other words, the arc sine of negative a half equals theta, which is negative pi 6, right, if you've forgotten that from trig. I have another one here. Let's do the tangent of the arc cosine of root 10 over 5. Okay. What I'm going to do first is let me just go to the side for a minute and let me just take the inside. I'm going to call this arc cosine of root 10 over 5. I'm going to call it theta. I'm going to solve that using the inverse again. So if the arc cosine of root 10 over 5 equals theta, that means the cosine of theta is root 10 over 5. Now this is where theta is between 0 and pi, right? If you remember, you had to cut off the original theta between 0 and pi in order for it to have an inverse, the arc cosine, okay? So if the cosine is positive, right, we have this positive cosine, it's somewhere between 0 and pi, right? But the cosine is positive, we know it's got to be, this theta's got to be in quadrant 1. And since cosine is adjacent over hypotenuse, we can fill it out now and use that reference angle theta there and solve for the remaining side. So root 10 squared plus b squared equals 5 squared. So b squared is 25 minus 10, which is 15. B equals plus or minus root 15. That's a positive sign in quadrant 1, so I'm going to label that root 15 there. So now that I've done this step here, right, I've been able to draw cosine. I'm going to go back now to this, my original problem, and remember, I've called the arc cosine, I called it theta, the arc cosine of root 10 over 5. So really, I'm just finding tangent of theta, and I have a picture of theta now. And tangent of theta, tangent's opposite over adjacent. So opposite's root 15, adjacent's root 10. Root 15 over root 10. Or in other words, if you rationalize that, root 15 times 10, so 5 times 3 times 5 times 2, there's the 15, 10, all over 10. So we got 5 root 6 all over 10, or root 6 over 2. That's what the tangent of the arc cosine of root 10 over 5 is. Okay, that's just a little review of our inverses. Now, the calculus part of this. So here's the derivatives of the inverse trig functions. Okay, the derivatives of the inverse trig functions. So you're going to I don't expect you to memorize these. You can look back at the formulas and use those as you go through. But I'm going to work through some examples here. The first one is the derivative of the arc sine of 2x. The arc sine of 2x. Now what we need to know is what's the derivative of the arc sine of u. Or same thing as the derivative, right? These are the same thing of u. So I flick back and I say, oh, it's 1 over the square root of 1 minus u squared times u prime times du dx times u prime. So chain rule on that. So I'm just going to follow that. I say, oh, okay, well, u is 2x. That's my u. So it's 1 over the square root of 1 minus u squared, and then chain rule. Since it's not just x, it's 2x, so I say, well, what's the derivative of 2x is 2. So this just ends up being 2 over the square root of 1 minus 4x squared. Right? 2x squared is 2 squared x squared. And that's the derivative of the arc sine of 2x. Let's do another one here. Let's take the derivative of the arc tangent of 3x. So it goes, I say, well, what's the derivative of the arc tangent of u? And I look back at my list and I say, oh, that's 1 over 1 plus u squared times u prime, right? In other words, chain rule on that u. So u is my 3x. So I have 1 over 1 plus u squared. Again, that's our 3x. Times chain rule. It's not just an x right there. So what's the derivative of 3x? 3. So this ends up being 3 over 1 plus 9x squared. Okay. Let's do some more here. Whoops. Looks like I better erase this. Let's do the derivative of the arc sine of root x. The derivative of the arc sine of the square root of x. Again, we know that the derivative of the arc sine of u, the arc sine of u, is 1 over square root of 1 minus u squared times u prime, right? In other words, chain rule on that. Now u is the square root of x, so here we go. This becomes 1 over square root of 1 minus root x is squared times chain rule. So what's the derivative of x to the 1/2? It's 1/2 x to the negative 1/2. Okay, so this becomes 1 over square root of 1 minus x. Square root of x is square root of x, quantity squared is x, right? Times, and this is 1 over 2 root x. So now we've got, let me rewrite this. I got 1 over, I'm going to put the 2 there, and then I got root x times root 1 minus x. Well, they can go all underneath the same radical, so x times 1 minus x, if you will, or distribute that x minus x squared. So 1 over 2 times the square root of x minus x squared. That's the derivative of the arc sine of root x. Okay, let me do one more here. Let's go derivative of the arcsecant of e to the 2x. Arcsecant of e to the 2x. So I need to know what the derivative of the arcsecant of u is. So I look on my list, and it's 1 over absolute value of u times the square root of u squared minus 1 square root of u squared minus 1 times chain rule derivative of u. This is where the absolute value of u is greater than 1. So this becomes 1 over absolute value of e to the 2x square root of e to the 2x squared minus 1 times derivative of e to the 2x. So that's ln of e to the 2x, derivative of 2x is 2. Okay. So this becomes, now the absolute value of e to the 2x, I don't need the absolute value on that because e to the 2x is always positive, so I can erase that. ln of e is 1. So on the top I've got 2 e to the 2x. Again, the absolute value of e to the 2x is just e to the 2x. And then here I've got e to the 2x times e to the 2x, or e to the 2x squared, right, is e to the 4x. Notice those e to the 2x's cancel. So I got 2 over square root of e to the 4x minus 1. And there's our derivative. Right? Here's just your solutions of those. And thank you so much for watching today. We'll see you guys next time.